Thank you everybody for joining. We really appreciate you taking the time, whether it's your morning, evening, or afternoon. This is our second talk in this international webinar series, and we're so thankful for Dr. Andrés Tassara for joining us and giving this wonderful talk. Before we get started, I just want to remind everyone that there's the Q&A feature that you can use to ask questions. We'll have time at the end to answer all of them, but you can feel free to type them out at any point during the talk. And we also have a closed caption feature that you can use if you so desire. The button for that is on the bottom of your video screen. I also want to remind everyone that if you want to suggest a future speaker in this series, we have a suggestion form on our website that we can include in the chat. Any suggestions for future speakers is very helpful to us because we want to make sure that these webinars meet the needs of this community. So without further ado, I want to introduce today's speaker, Dr. Andrés Tassara. Dr. Tassara is joining us from the Universidad de Concepción, where his research focuses on structure of the Earth's interior, focusing on Andean geology. He is a member of the AndesNet Executive Committee and is also the co-chair of SENet's Coordinating Committee, where his contributions have helped expand the reach of the SZ4D scientific community. We are thrilled to have him with us today and hope you will all enjoy his talk on the temperature of the Chilean Megathrust and its control on seismogenesis. So without further ado, I'm going to pass the floor or the proverbial mic to Andrés. Thank you so much.
Thank you, Juliet, for the introduction, and thank you for the invitation also to this exciting webinar series of SZ4D. In the coming 40 minutes, I guess, 40 to 45, I hope not longer than this, I will show you the work that we have been doing with some students, previous undergrad and graduate students here in the Universidad de Concepción over the last couple of years, understanding or studying the controls on the temperature in the Chilean Megathrust and how these affect seismogenesis of very large earthquakes here in this region. So let's start introducing this topic. For this, I will use this very simple scheme proposed by Tickler and Raff in 1993. So they based this view of the megatrust on previous works of some researchers, but not too much, I have to say. I mean, until the 90s, until the beginning of the 90s, there was not too much understanding of what was the temperature in the megatrust and how this can control also the seismogenesis. But starting in the early 90s with this work of Tickler and Raff, and then other workers after them, we started to understand. We started to give or to have a more ample understanding of the control of temperature in the seismogenesis of the megatrust. So what they propose in this paper is that the couplet, they call this the couplet zone. Now, all of us, we are talking about the seismogenic zone, but it's true that this should be couplet, should be coupling between the subducting slab and the forearc along this region. And this couplet zone is able to produce earthquakes. And this is mostly due to two different or, well, complementary, I will say, complementary factors that are occurring here along this region. No, one of them, as Tickler and Raff mentioned to us, is the stability slide or sliding stability field or the condition of sliding stability, no, with regions of unstable behavior inside the seismogenic zone, rounded by regions with stable sliding, where earthquake cannot nucleate, but it could probably propagate. So the nucleation and mostly propagation of earthquakes inside this region of unstable sliding, but this region also coincides with the region of higher shear stresses or frictional strength here along the megatrust. And we can do something now. We can try to expand a little bit this conceptual framework. It's gonna be useful during the rest of the talk. So I put just this scheme, I rotated in order to put it in that way, So now you can see more clearly what are the ideas of titular and rough, what's happening along the megathrust. No, we see that there is inside this region, the seismogenic region, this difference between stabilities or slight instability and the frictional strength. And now, over the years, a lot of literature has been written regarding the stability field or the frictional stability regime inside the seismogenic zone. For instance, this nice compilation of Phillips et al. In 2020 show us how along the seismogenic zone, what we see is that temperature really controls the value of A minus B parameter. What's the A minus B parameter? Well, this is part of the rate and state friction law. And this, in this very simple formulation of the rate and state friction law, we see that A minus B is quite important, because for A minus B, for values of these negative values of A minus B, for an increase in velocity with respect to the convergence velocity, a rapid increase due to an earthquake, if this parameter is lower than 0, that means that friction will be reduced. The dynamic friction will be reduced compared with the static friction. And that means that the earthquake can be propagated. That's the typical velocity weakening behavior. No? With an increase in velocity, we are able to weaken the megathrust because A minus B is less than 0. And that is what we can see here from a number or several different rock types. They tend to have this tendency between 100 and 350 degrees Celsius to be below 0. For values above 0, positive values, the contrary is true. An increase in velocity will create an increase in friction and will tend to arrest the seismic rupture. So for most of the people, they agree that 350 degrees C is the down the limit of the seismogenic zone because of this effect on A minus B. But it's also true that if we see also at the Gilstrand envelope, which is actually this figure here from Titular Rough, it's meant to represent the Gilstrand envelope. And here I just put the most common reference for this, which is Gibson Evans in 1979. But many people have worked on that. Actually, this is from our paper that we are preparing now. And what we can see here is that the variations in temperature control also the depth of the brittle ductile transition. Here we see that Gilstrand envelope is built with a brittle gradient, or where Gilstrand increases with depth, but at certain point the brittle ductile transition, the Gilstrand should be reduced with depth, because of the thermal dependency of the ductile Gilstrand. So we see here that with increase in depth, in this case, we will have an increase in the brittle Gilstrand, which is predicted by the Bayer's law, actually, and the ductile Gilstrand will be reduced. So at this point, we have the brittle ductile transition that is mostly for rocks, but it can be applied also for the megathrust, for the gauges inside the megathrust. And for most of the people, also, this temperature at which the transition is produced, well, it depends in many factors, as you can see here, but for most typical rock types along the megathrust, we will also agree that it's something similar to 350 degrees south. So that's an agreement between these two different views of what is controlling the seismogenic zone. It seems to be a very nice coincidence in terms of the rate and state frictional behavior, the A minus B parameter, and also the brittle ductile transition given by these flow laws. They tend to agree that 350 degrees C is the down limit of the seismogenic zone. And that has been integrated in many studies. And here we see a recent work of Ono Onken and co-workers, where they actually, refine, we will say, the three-dimensional view of the megathrust that we can see here. just in this case, comparing that with outcrops along the Alps, where we can see an exhumed megathrust, no? So along the megathrust or along the different outcrops, they find different mineral associations and also textures that are related with different range of temperatures. And with this range of temperatures, they were also able to constrain, in this case, from a very observational point of view, a geological point of view, what should be the temperatures also along the megathrust, which is very nice because that gives us a direct idea of what are the temperature controls on the different mechanisms acting along the megathrust, which is, well, and they also, of course, agree that 350 or between 100 and 350 C, we should have the the seismogenic zone. And they also compile this figure, no? They put this figure also in the paper where we can see the depth variation of the different textures and fault features along the substantial channel, very nicely represented for these different outcrops. And of course, we can also see that the megathrust, I mean, the seismogenic zone along the megathrust is limited by the temperature field. That also it's somehow related with the strength profile and with the stability field and with the pore pressure fluid also. So also very nice way to see how temperature controls the different stability regimes and the seismogenic behavior along the seismogenic zone. So now the question is how to in real subduction zones or present day subduction zones, I would say, how we can constrain temperatures, no? Because it seems to be very important, but it's not so easy to get some values to the temperature distribution of the megathrust. And for this, we have been using the approach of Philip England, and co-workers. That it's very interesting because that give us some analytical expressions that we can include or can incorporate in some codes, some simple codes for temperatures, heat flows, and frictional stresses along major thrust fault. That is the first paper in the 90s, actually, from Molnar and Engdahl. And we have been using these new formulations. This paper is for 2018, and this one from 2021, where they refine a little bit more these expressions and use it for estimating temperatures globally along the megathrust, along subduction zones along the globe. And we implemented that to make a detailed analysis along the Andean margin. And first of all, I will show you a little bit this formulation. I will use some time explaining you this analytical expression with this figure that we see here for a subduction zone. So it's the subducting oceanic plate, and that's the upper plate, in this case, a continental plate like in the Andes. And we can see that we can calculate the temperatures along the megathrust as a combination, as a simple combination, I will say, of many different parameters. So that's perhaps the problem. We have a lot of parameters to fix here in order to have one value of temperature at each position along the x-axis, no, along the megathrust. So let's see what are these parameters. So first of all, we have a ZF, no, it's the depth to the megathrust. That depends, of course, on the x direction. So SF is changing along or perpendicular to the trench. And we see here a first component, which is the heat flow from the slab. Heat flow from the slab that also depends on the age of the slab. No, we all know that for younger late ages, the higher will be the heat flow from the slab. And we also have here the shear stresses multiplied with the velocity along the megathrust. So that's the shear heating effect, no, for a moving plate and for certain frictional behavior here in the megathrust that is represented by friction and pore fluid pressure. We will have a given shear stress that we calculated here as dependent of the coefficient of friction, density, pore fluid pressure, and the angle. No, we are taking here that the normal stress is actually the weight of the Fourier arc on top of the megathrust, and along the or combine it, I mean, corrected by the angle of subduction. But it's very important, this one, because we see here that there are many effects that are included inside the shear stress. When you multiply that by velocity, give us some heat that is produced because of the friction. And the other expression here is related with the heat production inside the crust that is radiated toward the megathrust. It's a little component of heat that is radiated toward the megathrust in order to increase the temperature, but it's very important in terms of the surface heat flow, that it's a combination of what be produced as heat here in the megathrust and also produced by this component A, which is the heat production ratio, which is in this case multiplied by the depth of this of the layer where this where the radioactive elements are concentrated inside the crust. And well, that's the more important parameters here, but you can see also that it's divided by the thermal conductivity of the upper plate, but also for this parameter S, which is a reduction parameter introduced by England and co-workers in order to reproduce somehow the advection of cold geotherm because of the movement of the subducting plate. So without movement of the subducting plate, that should be the temperature along this interface, but we know that it is moving, so that should be reduced by this factor where we also introduce the thermal conductivity of the subducting plate and the thermal diffusivity. And it is also very important that this expression provide us with an expression for the surface heat flow, as I mentioned to you. And that's important because that's the parameter that we can compare with observations in order to constrain our models. In the case of the application that we have been doing for the Chilean Megathrust, we fixed most of these parameters. For instance, we calculated the heat flow from the slab just by an expression that used H from Miller et al. As a varied parameter on the margin. For the shear stresses, we just take one value of coefficient of friction of 0.65, which is the wireless friction. Most of the, it's for most of the rocks, or for all of the rocks along the planet, the relation between shear stresses and normal stresses gives you a value of friction of this order of magnitude. We also computed densities, average densities along the margin that change with the position. Based on the three-dimensional density model of Tassara and Chauer in 2012. We also take the deep angle from the slab 2.0 for 2.0 model, and also the velocities, convergence velocity taking this value. Most of the thermal parameters, we also just choose one common value. And it's important to mention also that the thickness of the radiogenic layer here also changed, and we take it from the density model of Tassara and Chauer. So both densities and the thickness of the upper crustal layer are taken from a model that includes not only gravity, but most of the geophysical data along the margin. And the only two parameters that we leave it free are pore fluid pressure ratios. We don't know what's the value of pore fluid pressure, and we also don't know what are the values of radiogenic heat production. Of course, we can take just a common value, but we choose to have these two different parameters in order to play a little bit with the model and see what are the interactions, or the better to say the balance between increasing the heat production radio compared what will be the effect of increasing the value of, for instance, of heat production in the value of lambda, for instance. No, we will play a little bit with this. I will show you in a minute how we implement this for the particular case of the Andes. So remember that our target is to calculate the temperatures in the megathrust, and we fix all the other parameters, but just leave free A, the value of A, the radiogenic heat production, and also the value of lambda inside the shear stress. And remember also that we will compare the predicted heat flow of each of our models with that we can calculate with this expression. We can compare that with the actual observed heat flow measurements in the Andean margin. So in order to start looking at the Andes, I will show you this figure where we actually have all the heat flow measurements that we have compiled over the last years. Well, and not all of them. So because, well, I will show you a little bit ample database, but here we can see all these points here, or these symbols. These different symbols are for different methods to measure the heat flow. Yeah, and we can see that we can see variation between 20 and more than 90 milliwatts per square meter. Meaning, of course, that higher heat values seems to be located more toward the south compared with the north, where we see lower heat flow values. And in the south, we also complemented these measurements with the very nice database that was given to us by Lucia Villar. These are not published measurements that are based on the bottom seismic reflectors that you can see in seismic lines. Bottom seismic reflectors are related with the concentration of carbon hydrates that have a given reflectancy and they are formed in particular condition of pressure and temperature that can give you also an estimate of the heat flow. So we can see also this database, and of course that means that here in the southern segment of the Chilean margin we have much more data that compared with the north. And there are also some important variations from north to south, not only in terms of the data, but also in terms of the tectonics of the area. For instance, the age of the subducting plate is much older in the north compared to the south. Actually, the Chilean triple action is some 200 kilometers southward from 45 degrees south. So a very nice gradient in the age of the Nazca plate that should have an effect also in this heat flow from the slab that will impact also in the temperatures in the megathrust. And we can also see impressive variation in climate. This is from Streger et al. 2007, where we can see the precipitation, the mean yearly precipitation with a very, very dry region in the north. There is the Atacama Desert, the driest place in the world, compared with the southern Andes, where we have a lot of rain. Actually, well, I live here in Concepción. Now it's raining. Has been raining like crazy during the last week. But in southern Chile, it's even more rainy. And that has a very important impact in the amount of sediments in the trench. So the trench infill is very thin in the north. Most of the people say that it's sediment-starved trench compared with less than 100 meters in some parts, compared with southern Chile, where we see thickness of more than 2 kilometers. And that should have some effect, of course, in the lubrication in the megathrust, and perhaps also in the value of lambda, the pore pressure flare, the pore pressure fluid ratio. Perhaps we can hypothesize that lambda will be low here in the north compared with the south, and should have an effect on the thermal state also. So let's see if that's true or not. And we will start looking at a particular model. All our models are parameterized in terms of the radiogenic heat production and the value of lambda. And this particular model, we are seeing a model with these values of these two parameters. And what is important for us now in this part of the talk is just it's not actually the values of these parameters. We have to choose some values. We can choose between an infinite range of values to have infinite models, but we just choose these values for this particular case. And what I want to show you here is how we can decompose the different contributions to megatrust temperature. So first of all, let's try to see at the map where we see variations in temperature between 0 and 700 degrees Celsius. Of course, we can see an increase in temperatures from the trench toward the bounded limit of the seismogenic zone. We are just taking here 60 kilometers depth in order to construct our model. We will see if that's it's comparable with the bounded limit of the seismogenic zone or not. And but we can also see some variations along strike, no, from relatively higher temperatures in the north compared to the south. No, you can compare that seeing the temperatures along the coastline. So here in the north, we see something like 500 to 600 degrees Celsius behind the coast, but in the south, that temperature is lower than 200 to 300 to 250 degrees Celsius. So there is a nice gradient in temperatures from high in the north to low in the south. Let's see why that's, what are the reasons for that. And we can decompose our equation, the equation that we are using in these three different components. So the first of, I will show you from less to more important contribution to temperature. So the lowest or the smallest contribution to the megatrust temperature is due to the variation in the heat production that we can see here. No, we see that the temperatures, the contribution to temperature is very, very small. It's on the order of some degrees Celsius, up to 15 degrees Celsius, probably here in these regions. No, it's really not important at all. So you could not use this effect that will be okay. Mostly compared with this, I mean, it's like 3 orders of magnitude lower or 2 orders of magnitude lower than the temperature that we see on the megatrust. But it is very important to include the effect of radiogenic heat production because it has a big impact in the surface heat flow that it's important, as we will see, to constrain the data, to constrain the models, no? So, okay, that's one contribution. The second one is due to the effect of heat flow from the slab. So it's what we see here is the effect of changing the age of the slab from north to south. And as you can expect, that means for younger subducting plate toward the south, we see higher temperatures in the megatrust compared with to the north. So that's good because that's what you will expect. But note that the temperatures, well, are 10 times larger than the temperatures produced by the previous effect, but still very low compared with the total temperature. Yeah. So the effect of the slab heat flow is on the order of 1/4 of the total temperature of the megatrust. No, it's not so important compared with the most important effect or contributor, which is the shear stresses. No, shear stresses are by far much more important than the other two components. No, and as you can see here, from what variation between 0 and 600 degrees Celsius. And which is very interesting is also the along strike variations of this effect, because as you can see here, is higher temperature in the north compared with the temperatures in the south. That is why we see in the total temperature this same variation, no? With high temperatures to low temperatures when you go from north to south. And why that is true? I mean, what's the main reason for this variation in the shear stress effect on temperature in the megatrust? Well, that is mostly due to variations in the shear stress, of course, because the velocity doesn't change, and these other parameters also are kind of fixed. This is fixed, but this one changed a little bit because of the change in the angle, in the deep angle, but not too much. Most of the changes are due to the change in shear stresses that you can see here. No, for instance, with relatively high values in the north compared to the south in the offshore megatrust. And that is mostly due to changes in our formulation, to changes in density from north to south, no? All the other parameters are fixed, no? But we leave density to change along the margin, and that's constrained by the density model of Tassara and James, the model that we published already 10 years ago, where we have an estimation of the average density of the forearc. And as you can see, density is much higher in the north compared to the south, no? Mostly along the offshore region, but also in the onshore region, no? In the offshore region, with perhaps some exceptions here in this point and here, most of the forearc is low density compared with the higher density in the northern part of the Chilean margin, no? That these values of densities are here in kilograms per cubic meter. So that's an important constraint, I would say, and it's an important result to see how relevant is the effect of shear stresses in the temperature, much more relevant than the other contributors, but also that the variations in density along the margin are very, very important in terms of impacting on the temperature and the megathrust. And for this particular model, I have to mention that the predicted heat flow, surface heat flow of this model has a relatively good fit to the observer surface heat flow measurement. So what we did is to calculate the root mean square error between the measurements and the predicted heat flow at the position of each measurement, no? It's taken all the data along the Chilean margin, all the data that lies, of course, above this region that where we are computing the model. And for each of these positions, we calculated the predicted heat flow and then make the subtraction between them in order to calculate their root mean square error. And in this case, this error is of the order of 15 milliwatts per square meter, which is lower than the average error of the measurement. So that's that's why this one is a good model. But as I mentioned, we can make a lot of different models changing these values between some expected range of variation. And that's what we did, but not for this particular model along the entire margin, because we actually divided or separated the Chilean margin in north to south. That is mostly because, well, we already observed this difference between north and south in terms of temperature, and we noted also the difference in the heat flow database. We have much more data here in the south compared to the north. So when we made a model using all the data, we are biased toward the southern part of the margin. Remember that here we have all the other BSR-based heat flow measurements provided by Lucia Villar. So we have much more data here in the south compared to the north. But we also have to mention the main tectonic difference between north and south that justify doing an analysis where we can separate these two segments. And we did that, and we computed a number of different models for the northern segment and for the southern segment, and the final result is here. So what we are seeing here, we are seeing a graph where we have the heat production, the modeled heat production in the x-axis, and the pore fluid pressure ratio, the modeled one, also in the y-axis. And here we are seeing the results of more than the order of 250 models for the southern region in blue and for the northern region in red. So for each of the region, we have 250 models. At the end, we have something like 500 different thermal models with changing values of these two parameters. So one particular, that this particular model on the entire margin, will be a model, if we go back here to see what are the values of lambda and A, so that model will be located somehow here with 0.9 for lambda, and with something like 2.5 here for A. It's somewhere here, this model, but we have a lot of different models for both segments. And we end up with this nice graph where you can see the RMSA value, no? So each of these contour lines, for instance, for the south, no, where we can see that the lowest root mean square error are located here, are of the order of 11.2 milliwatts per square meter. And if we go in that direction for increasing A and increasing lambda, we have increasing values of the RMSA. No, that's true for the both models. But this increase is not so big. I mean, in this direction, the increase is the minimum compared with going in that direction. No, if we go far away from this line here, with models that lie, for instance, here, where you have a lot of heat flow generated by the heat production, and also a lot of heat generated by friction because of the very low pore fluid pressure. That means that the value of friction will be very high. I mean, value of the friction, when you multiply the value of 0.65 with the pore fluid pressure radio, no, will give you a lot of heat. So that means that you will go very far away from this line here. That's how we can read this. So all the models that lies, for instance, in the south, that lies along this line are good models. No, the best models in terms of the fit to the data are toward the very low values or near zero value for the heat production. That is true for the two models. What's the reason for that? Well, that is because if you remember the effect of heat production, it's multiplying by this parameter with the depth of the upper crust. And because in the model of Tassara and Echaurren, the depth of the upper crust has a lot of noise, to say a lot of spatial variation, did introduce also a lot of noise into the measurement of the root mean square error. So meaning that if we reduce this effect, the models are better in this term. But please remember that all these models are good, all the models that go around this line, because they are not so different in terms of the RMSI. Other things that we can see here that are that the tendencies between north and south are quite different. No, so first of all, in the north, the values of RMSA are much higher than in the south, and that is mostly because of the lot of variation of the heat flow here in the north compared to the south. No, we can see values of very low heat flow and very high also. But also we don't have too much data here in the north. That means that the RMSA values are much broader and much higher than compared to the south, where we have much more data and a better defined tendency here. But we can see also that the variations are quite interesting. For instance, if we assume that the value of A is the same from north to south, so for instance, let's put here in 1 microwatts per cubic meter. So that means that in the south, the value of lambda will be of the order of 0.81. But in the north, we will need a much higher value of lambda. No, that is interesting. I mean, if we either assume that A is the same from north to south, if we assume that, we have to assume that the lubrication is much higher in the north compared to the south, which is something crazy. It's something that it's not well constrained or doesn't fit too well with that variation in the trench infill from north to south. But if we assume that, for instance, the other way, that the pore fluid pressure ratio is the same from north in the north compared to the south, well, in this case, if it is the same, we have to accept also that the A value will be much lower in the north compared to the south. So meaning that we have low heat production in the north compared to the south. We will see in a minute that this is quite it's well fitted with the geology of the Andes. So that's mostly the situation. So okay, that's very interesting. That's tell us a lot about comparing the heat flow data with the predicted heat flow can give us a lot of information about changes in parameters from north to south. But in the next slices, we will see some particular models for the south and from first for the north and then for the south along these lines of more or less equally well-fitted heat flow data. No, we will see 5 different models in the north and the south with different values of A and lambda in order to see what is the main effect on the seismogenesis. So that's what we see here in the north first. For each of these maps, we are seeing temperatures in the color, and you can see also the values of A and lambda for each of these different models. No, so first thing that we have to note, how temperatures really change a lot when we change these values. No, all of these models, as you can remember, are more or less equally good models in terms of fitting the heat flow data. Yeah, as I mentioned, perhaps this one is better than the other ones, but the difference is very, very small in terms of changing the root mean square error. All of them are good models to say, but the temperatures are quite different. No, why is that? Well, of course, because if we don't put heat generated in the crust, we have to create a lot of heat in the megathrust. So, and that means that in this case, no, values of lambda of the order of 0.8, what are very, very high compared with estimates for other sources. So if we have low, excuse me, it's very, very low. No, it's a low lambda, meaning high friction, and with high friction we have a lot of shear stresses created in the megathrust, and that's why we see these very high temperatures here. And here in white, this white line here is the 350 degrees Celsius isotherm. No? So this isotherm should show us where the down limit of seismogenesis is. And if we compare this one with the other extreme, where we have a very high lambda, no, with a very high lambda, the value of effective friction is very, very low, of the order, in this case, is of the order is 0.05, more or less, very, very low effective friction, meaning almost no shear stresses here, and that means very low also temperatures. Actually, the 350 degrees C isotherm is even far away from here. I mean, it's deeper than here. We are seeing here temperatures of the order of only 200 to 250 degrees C. So very low temperatures due to a very high lubrication of the megathrust, implying that in order to put more heat to compensate for the heat flow, we need a much higher value of the heat production. So, and that's what we see here. We see that variations with increasing values of lambda and increasing value of A, we have a lot of difference in terms of the temperature, but with this more or less the same fit to the heat flow data. So despite this small difference in the root mean square error between these different models, which one is the best model? I mean, how to really select a model, not only based on the RMSA, but also in some seismological information. And for that, we computed, or we estimated the depth to the or the down dip limit of seismogenic behavior, no, using the earthquake from the CMT catalog and calculating the depth at which the density of earthquakes with reverse focal mechanism decrease below a certain level. And with this, we have this blue line here that we extracted for this analysis, and we discretized this blue line now here in these white points that you can see here. No, all of these points show you the depth at which, or are selected in order to show the depth at which the focal or the reverse focal mechanism earthquakes really decrease toward the east. And so what we want to see actually are models where this 350 degrees C line, which is the white line here, really goes through all these points, like here, or this other model also here. Perhaps this model is better in this case. But for that, we better calculated histograms. So we take all these points, we calculated the temperature for all the models and put that in a histogram. So What we can see here is that, for instance, for this very hot model, most of these points are at temperatures between 400 and 800 degrees C. And for cold models, all these points are between 100 and 300 and 250 degrees C. So too hot, too low temperatures, too high temperatures. But for this model here, these two models are good models in terms that the temperature at the down limit calculated from this method, it's on the order of 350 degrees C, no? The 350 degrees C, something like this. So this model is a little bit too cold, and this one is perhaps a little bit too hot, no? So the best model is something in between, no? Something where these values are in between these two values here. We did the same for the southern segment now, so you can see more or less the same. And you also see that temperatures here is too hot for the DDL in this case and too low here. And we also select something in between, no? Something more closer perhaps to this one, to this model, compared to this other model. So that's the way how we selected our preferred models between the many different possibilities that give us our approach. So our preferred models are this one at the end, no? For the south, it's a model where we have a value of heat production of the order of 4 microwatts per cubic meter, and lambda is of the order of 0.91, whereas in the north, the values of A are much lower than this one, of the order of 2.5 microwatts per cubic meter, and lambda is somehow similar. It's a little bit lower compared to the south, but more or less at the same order of magnitude. So from this we can extract some conclusions. For instance, this rather small variation in lambda between 0.81 and 0.91, that are really tiny changes in the pore pressure ratio, implies that there are similar lubrication conditions despite of different trench infill and mass transfer mode. No, so because northern Chile is sediment starved, most of the people say that it's a erosive margin, compared with the south, where we have a lot of sediments in the trench and a accretionary margin. But from this image of Cliff and Manucci, we can already see that independent of the mass transfer mode, we see that along the subduction channel, we should have kind of sediment somehow, no? Either material removed from the upper plate that it's lubricated with water, and sediments that come with the incoming plate, and also here in the trench. But most of this material is somehow incorporated here, creating some lubrication. Of course, here in the south, you should expect much more lubrication because you have a thick pile of sediments that can be undertrusted. But our results seems to reflect that these lubrication conditions are similar from north to south. If we believe that these differences are true, no, that is also good because, well, as you can see here in the north, we see a lower lambda compared to the south, no, meaning that it could be possible to have a higher lubrication here in the south compared to the north, but it's very tiny variation. We don't know if that's true or not. We perhaps need more data, more heat flow data in the north in order to better constrain these variations. And the second message for these two models here is that it has a significant variation. Now, this variation between 2.5 and 4 microwatts for cubic meter are important. It's something that you can see in the rock types, no? And this means different crustal composition from north to south, no? You can see that here with a value of 4 here in the south, we need something much more felsic compared to the north, no? Because felsic rocks tend to concentrate much more radioactive elements that give you a higher radiogenic heat production compared to the north. So that this has a very important implication of felsic in the south compared to mafic in the north. And that's actually what we see here in this graph. So I take it just from Molina et al. 2021, a paper with my PhD student Diego Molina, where we compared the surface geology of the margin with gravity, higher gravity, meaning in this case higher density, and that's the density from the density model of Tassara and Echaurren. So you can see that hikes in the gravity anomaly, in this case, if the Fourier gravity anomaly, only effects due to change in density inside the crust. No, so there is very, very nice correlation: high density in the north, low density in the south, and this variation in density quite nicely fits also variations in density of the rocks that you can see here from a compilation of the geological map of Chile. And these rocks here that are intrusive rocks, granites, volcanic rock from Jurassic to lower Cretaceous ages are actually diorites, gabbros, and basalts from the early Andean subduction arc here in the north. Whereas toward the south, what we see at the surface are granites, mostly granites, perhaps tonalized granodiorites, but intermediate to felsic composition, intrusive rocks of the Paleozoic volcanic arc, and also metamorphic rocks that are metapellites or metasediments with some inclusions of metabasalts, but dominantly metasediments also of low density and low heat production. No. So that's a very nice result, I think, to really to constrain the variations in A using this method that and this constraint or these values implied by our method really coincide very nicely also with variation in the geology of the margin that we can see at the surface. So with our preferred models here, and that's one of my last slices here. That's the preferred model in the north and the preferred model in the south. And what we see here now in magenta are seismicity from the CSN, from the Centro Sismológico Nacional of Chile, between years 2000 and 2024, and also the slip distribution of large earthquake like the Iquique earthquake in 2014, magnitude 8.1, the Illapel earthquake of 2015, magnitude 8.3, the Maule earthquake of 2010, magnitude 8.8, and the giant 1960 Valdivia earthquake, magnitude 9.5. And in black, you see the 120 degrees Celsius isotherm, and in white, the 350 degrees Celsius isotherm in both different regions. And it's very nice to just to see how all the seismicities tend to be concentrated in these two temperature limits, and also most of the large slip regions in these 4 earthquakes are concentrated also inside this region, inside this temperature range. No, we can see that now also with this histograms for the north and south. No, this histogram in the north, it's show us in the histogram the frequency distribution of earthquakes at different temperatures, no, in these two diagrams, and the points are the earthquakes, the magnitude of the earthquakes also against temperature. So we can see that the up dip limit of the seismogenic zone, is quite well represented by this very strong change, very strong decrease in the amount of earthquakes when we go up to or from 150, 120 degrees Celsius to lower temperatures. We see much less earthquake compared with the range that we see inside this region. And the 350 degrees C, which is something like this, give us an indication of a strong also decrease in the amount of earthquake when we go to higher temperatures, but it's not that striked, no? It's not so well defined, I would say, compared with the up dip limit. No? Mostly here in the south, it seems to be very gradual change in the number of earthquakes with increasing temperature. Yeah. And here in the south, we see something quite interesting, because the 350 degrees C really make a change, but we also see some concentration of earthquakes at higher temperatures. And most of the earthquakes are actually related with aftershocks of the 2010 Maule earthquake, actually. Many other authors have shown that there is this band of a lot of aftershocks very deep in the megatrust. And that's what we can see here. That's it's an interesting observation also, this difference between north and south. You can also see that the magnitude of the earthquakes tends to be higher, of course, also in this range of value between 120 and 350 degrees Celsius. No, most of the earthquakes are there, and the magnitudes are also higher inside this value, inside this range, which is what you will expect. And we can also see the coseismic slip. So here for each of the earthquakes, we discretized the grid in a grid, no, and calculated for each point of the grid inside the region where we have coseismic slip higher than 0. We also calculate the temperatures, and we make the same. I mean, it's the same kind of histogram, but now for the slip, you can see also that it's not that straight like here. No, here is very, very marked. The most of the points, no, or between 20 and 25% of all the earthquakes are or more. I mean, in this case, it's like 90% of the earthquakes. No, so that's only this range is 25, 23%, but it's more than 95% of the earthquakes are nucleated inside temperatures between 120 and 350. But for the slip, it's not that clear. I mean, it's more homogeneously distributed inside this range of temperatures. But what is very interesting is that the slip is also changed a lot. No, for instance, here for the Valdivia earthquake, we see that the very, very large slip of the order of 45 meters. No, it's a huge slip here in these regions are inside the same temperature range. And when we go to higher temperatures, the slip really, really decrease to almost nothing here for higher temperatures. So it also shows us the very important role that you will expect, of course, of temperature in controlling not only the point of nucleation of the earthquake, the epicenter, but also the amount of slip that you can get. So my take-home message for today will be this one. These analytical expressions are easy to implement and very useful. We can run hundreds of models in just 1 second or some seconds in a normal computer, and that gives us a lot of opportunities to really understand the temperature control on the megatrust. This temperature is largely dominated by shear heating. I think that's a very important message also, which itself is controlled by spatial variation in Fourier density. So if we have, like in the case of the Andes, a good estimation of Fourier density, that is very, very useful in terms of constraining the temperatures in the megatrust. So minimizing the difference between observed and predicted surface heat flow allow us for selecting optimal families of models, of families of optimal models. That is very important. That means that you need also surface heat flow measurements in order to constrain this model, because other than you can select whatever you want in terms of the frictional parameters. And assuming that the seismic DDL is controlled by the 350C isotherm, implies some important variations between these parameters between North and Southern Chile. Can help us to constrain these parameters, but also can show us the difference between these two. And these variations show or implies that implies for us similar megatrust lubrication conditions from north to south, quite similar. So there is no effect of Fraima and trench infill on lambda, and are very consistent also with the upper plate geology in terms of the values of A. And finally, seismicity and slip of large earthquakes is well restricted into the range that you will expect for this. So we demonstrate that for the particular case of Chile, the seismogenic zone really exists between this range of values. But this analysis allows us also to constrain some very important parameters for the rest of the margin. So thank you very much, and I'm very open to your questions.
Thank you so much, Andrés. I want to remind everyone that the Q&A feature is open. So if you have any questions, please feel free to type them there or in the chat. And also, I realize we're at the top of the hour now. So if anyone has to head off to their next meeting, you can always feel free to email your questions to us, and we can make sure that we get an answer for you. I will put that email in the chat right now, as well as I'm going to put the link for the suggestion form in case you want to hear from other speakers in the future. So with that, thank you so much, Andres. And the Q&A feature is still open. We'll give people a couple minutes to type in their questions. Okay, we have a question from Eric Dunham. The model has two assumptions worth discussing further. One, constant lambda independent of depth, and two, conductive heat flow rather than advective transport by fluid flow. Thoughts on whether these are appropriate?
Yeah, well, that's not completely true. For the second one, these equations actually include the effect of advection. So that's the nice thing with these equations. No, the effect of advection is actually concentrated as S parameter, which is a reduction. It reduced the heat flow, or it reduced the temperature also because of the advection. No, and these authors, mostly in the paper of Engdahl and May, they demonstrated using numerical models also that this very simple way to consider advection actually allows you to nicely reproduce the effect of the movement of the slab. And the first one, we are using just one value of lambda independent of the depth. That's true. And if we see here in the actually we can use this one. This is scheme of Onken et al., where you can see that lambda is in blue here. It should change a lot with depth. No, that's true. It should change a lot. But what we are mostly concentrated in this with this approach is that it's in this portion. No, in this portion, of course, lambda will be high here and high here because we have a lot of, or could have a lot of fluid release in the upper part of the system and also in the lower part of the system. Where much of the water from the slab is being released at that depth. But inside the seismogenic zone, it seems to be a good approximation just to assume as the same value of lambda. Yeah, we can perhaps implement something different, but I will not suggest that. I will not support that at this moment, because that introduces another parameter, which is how you will change these values of lambda across the strike. It's not so easy to do that and to have another way to make these constraints. But thank you for the question.
Thank you. We have another comment and question from Juan Diaz Naves. To better constrain the model, is it only necessary to have more heat flow measurements on the continental margin, or in addition off the trench axis on the oceanic plate, and how far offshore?
Yeah, good question, Juan. Thank you. Yeah, that's one of the points that perhaps I should reinforce more. I mean, we really need more data in the north. No, I don't think that we should try to get to the same coverage of the data from north to south. No, it's in order to really to make this analysis and other analysis that can be done by other people or by our own group. Will be so nice to have also the same cover of data. I mean, the same density of data in the north compared to the south. I think that is much more important to have it between the trench and the coast. No, probably have heat flow data in the onshore region is quite complicated, because in order to have very good data, we need to do it in boreholes, and there are not too much boreholes available. Also long boreholes where you can put a probe to measure the temperature. But in the onshore, it's not so complicated. No, I mean, it's complicated. Of course, you need to go with a chip and everything. But I think that for common chips and common cruises also here in this region, because of the SZ4D project. I mean, that's the region where the SZ4D project will be concentrated in the future. And I think that we can make an effort in order to have more data here in the onshore offshore region of this part of the margin, mostly where we don't have any data. That can be done just by with gravity coring. You can introduce a temperature sensor, and with this one, and depending on the depth of penetration, you can calculate also the heat flow. But I would say we will need also to put some efforts also in trying to see up bottom seismic reflectors here in the north. It's something that I already talked with Eduardo Contreras Reyes, perhaps in the next cruises, and also looking at all data we can recognize some BSR and increase the amount of data here in the north. And in the incoming plate, it will be very nice also. I think that it's also important because we need to constrain until which extent also the estimates that we can make from the age of the slab are well constrained. I mean, we are assuming that there is nothing like hydrothermal circulation before entering the trench that can reduce the heat flow. And that's something that it's not to occur, and will be very nice to have some measurements. And I would say until the Forebulge will be okay, because that's the region where we have most of the fracture zones that can allow for the circulation of fluids and reduction of the heat flow. Yeah.
Thank you. And then we have one more question. And I think since we're at 10 minutes past the hour, we'll make this our final question. But from Roberto Gonzalez, is QS directly proportional to slab age?
Yeah, absolutely. Q is, which is this one here, is inversely proportional to slab age. Yeah, it is. I mean, if you increase the age, if you decrease the age, you increase the slab heat flow. So it's reversely proportional to the slab age and has a dependency of the square root of the slab age. So that means that it's not linear. I mean, when you really reduce the age toward the southward, in the case of Chile, toward the triple ejection, the heat flow is increased a lot because of this effect. Yeah. So thank you everybody for your questions. And if you have more questions, please just contact me, and I will be very happy to answer that.
Thank you so much, Andrés, for that fantastic talk. And thank you everybody for taking time out of your day to come join us. We really appreciate it. And without further ado, we hope you have a great rest of your day. Thank you.
Yeah, thank you. Bye-bye.
Bye.